What is going on, everybody? Mr. Suffering here, and today I would like to talk about force vectors. So let's get to it. Okay, the purpose of adding force vectors is to determine the net force acting upon an object. Okay, so again, the purpose of adding force vectors is to determine the net force acting upon an object. Um, let's just, for an example, if you've ever seen tension cables or guy wires stabilizing a tower, or a pole, um, or any kind of structure, the wires work together so the tower does not fall in any direction. Okay, as long as there are no external forces and the wires are equally spaced, each wire should experience equal amounts of tension. Okay. Um, the tension in each wire can be expressed as force vectors or as a force vector. Um, it's imperative that engineers have values of these force vectors so they can make necessary decisions as to how much strength each tension wire or guide wire support as they support their mechanisms. Okay, so as we talk about force vectors, what I want you to take away, or I want you to know, that when you are expressing a vector, vectors has both magnitude as well as direction. Okay, and there you have it on my slide. Okay, again, force vectors, or a force vector, has both magnitude and direction. Okay, because we are looking at forces, the magnitude is going to be the length of something um, in your diagonal line, or it's going to be measured in pounds or newtons, because it's a force. Okay, um, the direction is just which way the force is going. Okay, so again, force vectors has both magnitude and direction. And the way you notate a force vector is just an arrow over the letter as to what you are naming this vector. Okay, so let's go to the next slide. Um, Regarding force vectors, there are three components or three parts that make up vectors. Firstly, the first there's the magnitude, which is the length of the line segment. Secondly, the next part is direction, and lastly, there's sense. So there's three parts of force vectors: magnitude, direction, and sense. And magnitude is basically the length of your line segment. In this example on this slide, the line segment is divided into three parts. Therefore, the magnitude of this vector is 3. Okay. You can also say that the vector is 25 pounds or 5 newtons. So you will see vectors in that way as well. So you'll see vectors as a line segment, as well as in pounds or newtons. So the number you're going to see with the line segment is going to be, the length or the force. So next, you have direction. Okay, the direction, it has two, or it has three components rather. It has the axis of reference. It has the degrees, as well as which way, whether it's clockwise or counterclockwise from the x axis or the y axis, etc. With direction, you must have a reference angle, and that is the positive x-axis, the negative x-axis, etc. You also must have degrees from that axis. And in this example, if you see my slide, this example of this vector is 30 degrees counterclockwise from the positive x-axis. So not only vectors have magnitude, it not only has direction, but it also has sense. And sense can be kind of confusing. It's very easy to naturally think that sense is direction, but it's different. Okay, so sense has two components. You can have a vertical sense as well as a horizontal sense. Okay, so in this example, what you would, since the sense has two components, vertical and horizontal, you want to start from the origin. Okay, so if you take a look at my arrow, this is our origin of our force vector, and looking at where the force vector is going at the tip of the arrowhead. So you need to know, where you're starting from and where you need to go. And since the sense is made up of two components, your vertical and your horizontal direction. In this case, you would say the sense of this vector is upward and to the right, or I would say this example, to the right and upward. Okay, so again, the big question you want to ask yourself with regards to sense is, you want to just look at where the arrow is versus where you started, and where you're going, and how do you get there. Okay. And in this example, you will see, the force vector in red, and you will see the sense. And how do you get to the tip of the arrowhead? Well, starting from the origin, you would go to the right on the positive x-axis and up on the positive y-axis. And take a look at this force vector. How do I get to the tip of the arrowhead? Well, I would go right on the positive x-axis and down on the negative y-axis. And these are also two examples, okay? Okay, so let's review some trigonometry. We know that this is a right triangle. There is a 90-degree angle, and the sum of all the interior angles must equal to 180 degrees. Therefore, we know that we are going to have two other angles that is going to add up to 90 degrees to guarantee that all angles are equal to 180 degrees. Let's go to our next slide. And on this right triangle, the longest side of our right triangle is our hypotenuse, and the other sides are the opposite and adjacent sides of the right triangle. And if you want to find the values of all the sides of this right triangle, you would use the Pythagorean theorem. A squared plus b squared equals c squared. Okay, so if you see the trigonometry functions, you have SOHCAHTOA. And what SOHCAHTOA means is basically, just a phrase to help you remember what it actually means. So if you take a look at SOH, S-O-H, this means that this S stands for sine theta. So it stands for sine, whereas your opposite is over your hypotenuse. So that is the equation for your sine theta. And CAH, C-A-H, means cosine theta, or cosine, your adjacent side of your right triangle over your hypotenuse. And you have TOA, T-O-A, which is your tangent theta, or tangent equals your opposite side over your adjacent side. And if you wanted to find the values of this, and you have your angle and your hypotenuse, you should be able to determine what the value is on the relative sides of this right triangle based on these trigonometry functions, okay? So let's take a look at it. Our hypotenuse will be typically our force vector. Our hypotenuse is the magnitude, which is the force, okay? And in this figure here, you'll see the adjacent side and the opposite side. And basically what those sides are these sides are the components of our hypotenuse. So we would call our adjacent side the component force X or Fx, and you'll see our opposite side as component Fy. And why is this the opposite? Well, you want to look at where the angle is, and component Fy is opposite the angle, and our component Fx is adjacent of the angle. Okay, so there we have it. All right, this slide right here, if you wanted to find the value for the opposite side, we would use sine or so, which is sine theta equal your component Fy over your hypotenuse, which is F. Okay, and if we do some simple algebra and multiply F from both sides, you would solve for Y, Fy, which is your force times your sine theta. And if you wanted to find the value for your adjacent side or force component Fx, you would use cosine Fx divided by your hypotenuse or force and do some simple algebra, and you will solve for your Fx. All right, and take a look at this caption in blue. Okay, Fx and Fy are negative if left on the x-axis or down on the y-axis, respectively. Okay, so don't forget that. Okay, so what you have right here, you have a vector, and we call this vector A, and the magnitude of vector A is 75 pounds. Okay, the first thing you want to do when you're finding the net force of a vector, the first thing you want to do, you want to determine the magnitude, the direction, and the sense of your vector force, okay? And in this case, your magnitude of vector A is 75 pounds, okay? And the direction is 35 degrees counterclockwise from the positive x-axis, okay? And the sense is to the right and up. Okay, so now that we have determined our the magnitude, direction, and the sense of force vector A, now the second step is to solve for the component forces of vector force A, okay? And we're going to name these components force AX and force AY, okay? And if we're going to solve for force AX, we're going to look at our SOHCAHTOA formula. And since we know that component force AX is adjacent of our angle, we're going to use cosine adjacent over your hypotenuse. So cosine theta equals force AX over your hypotenuse. And if you do some simple algebra, now you have force AX equals 75 pounds multiplied by cosine theta to the right. And you should get force AX equals 61.4 pounds. Okay, now that we have solved for component force AX, let's do the same for component FAY. And notice that since component force AY is opposite the angle, we're going to use our sine theta. Okay, so our sine theta equals your opposite side over your hypotenuse. And you have force AY equals 75 pounds times sine 35 degrees up. And when you do that calculation, you get component force AY equals 43 pounds. Okay, so now that we determined the magnitude, direction, and the sense of force vector A, we solved for the component forces. Now it's asking us to do the same thing with vector B, okay? So I'm not going to spend much time explaining how we've gotten the component forces for vector B. So let's just kind of just slide through these different slides. Okay, notice that our opposite side of component force BY is going down. So that will be a negative. So force BY is negative, and our final result will be negative 43 pounds. Okay, so now that we have determined the magnitude, direction, and the sense of force vector A and B, we solve for the component forces. Now, we want to draw a free body diagram of component X and Y, or A and B actually, of the force vectors. So let's go ahead and just do that. Okay, so here you have vector force A and vector force B. And if we draw the free body diagram of the components of those two vectors, here's what you have. And before you draw the free body diagram of the component forces, here's what I would like for you to do. List the forces according to sense, label right and up forces as positive, and label the left and down forces as negative. Okay, so before we draw our free body diagram, I like to draw this table right here. I would list out our X components. So here you see component AX and component BX, both at 61.4 pounds. And then you see our Y components. Our component force AY is positive 43, and our component force BY is negative 43. All right, now that we have determined this, I would draw the free body diagram based off of what we have listed right here. So notice we have for our X components, A and B. We have our Y components, positive 43 pounds, negative 43 pounds. Okay, so now that we have drawn a free body diagram of components A and B of our force vectors, now we need to find the resultant force by summing components A and B of our force vectors. Okay, so let's take a look. So here's our sum of fx formula, fax plus fbx, and we have 61.436 pounds added together, and we have 22.9 pounds going to the right, okay, according to our free body diagram. Now take a look at our component force y. These cancel out, so the sum of component force Fy is 0. So therefore, the magnitude of our force, our resultant force, is going to be a magnitude of 122.9 pounds. And the direction is 0 degrees from the positive x-axis, and our sense is to the right. All right, so our next step is to draw a free body diagram of our resultant force. Okay, guys, in this example, I would like to go over finding the resulting force of vector C and vector D, because we did not complete all of the steps, and I want to model this for you and kind of just go through steps 4, 5, 6, and 7, where we would take the resultant force components of our vectors and find the magnitude of our resultant force. So let's get to it. Okay, guys, take a look at vector C and vector D. Vector C has a magnitude of 300 pounds. Vector D has a magnitude of 400 pounds. So let us go through the steps. First thing I want to do is let's focus on vector C, okay? And our first step, determine the magnitude, direction, and the sense of force vector C, okay? So I'm going to, let's just draw another line. We're going to say this is vector C, 300 pounds, and our magnitude equals 300 pounds. And our direction, all right, so if I draw my components, so we'll say this is our X component right here. So this is force Cx. We'll say this is component force Cy. We'll say our direction is to the right and up. Okay. All right, so now that forgot our sense. I'm sorry. Our sense is right enough. Our direction is 60 degrees. Direction is 60 degrees. counterclockwise from the positive x axis. Okay. Now our sense is right. There we go. Now we're going to solve for our x and y components. Okay. So starting with our x component, we know that our force FAX is our adjacent. It's adjacent to angle. So we're going to use cosine theta. Cosine 60 degrees equals adjacent FCX over 300 pounds. Okay. And we can very well say that this is force CX equals cosine 60 degrees times 300. And CX equals 150 pounds. Let's see that again. Cosine 60. Yeah, 150 pounds. Now that we have we solve for component FCX, let's go ahead and solve for component FCY. So we know that FCY is opposite the angle. So we're going to use sine. Sine 60 degrees equals opposite force CY over 300 pounds. We have force CY equals sine 60 degrees times 300 pounds. Typically, I would say this will be sine 60 degrees up. Okay. And force CY equals 260 pounds. Okay. Now we're going to do this exact same thing for vector D. Okay. So we're just going to draw a free body diagram of vector D. Just going this direction. So our angle is 30 degrees. Okay. Now, what's our magnitude? Our magnitude is 400 pounds. Our direction what is our direction? We're going to say to the right. And we're going to say down. So this is force dy. And this is force dx. Okay, so our direction is 30 degrees clockwise from the positive x axis. In our sense is to the right and down. Zoom in just a little bit. All right, now our second step is solve for the component forces. So we have our F dx, and that is adjacent from the angle. So we're going to use cosine. How about this? We're going to say F dx equals cosine 30 degrees right multiplied by 400 pounds. That would be 350 pounds. Okay, we have F dy. Since that's going down, that is a negative force dy. Okay, so negative force dy equals sine 30 degrees down times 400 pounds. All right, and F dy equals negative 200 pounds. Okay, now that we have determined the magnitude, direction in the sense of force vectors C and D, we solve for the component forces. Now, let us draw a free body diagram illustrating the components of our force vectors, okay? Let's do that. Okay. May have to get another sheet of paper. Okay, so we're going to draw our x-axis. What I'm going to do first, I am going to draw my table. We're going to call this Fx. And we have Fcx, and we have Fdx. And Fcx equals 150 pounds. Oops, can't see that. Equals 150 pounds. And Fdx equals 350 pounds. Okay. Now let's start Fy's. Okay, so we have Fcy, we have Fdy. Fcy, bring it back to the camera, equal 260 pounds. And Fdy equals negative 200 pounds. Okay, so now that we have that, let's go ahead and draw our free body diagram. And we'll start at the, well, let's start at the x-axis. We'll draw a longer arrow for force dx because the magnitude is greater than force cx. So this has force dx. We have force cx. Force cx equals 150 pounds. And force dx equals 300 pounds. 350 pounds, actually. Okay. And let's take a look at force cy and force dy. Okay. So force cy equals 260 pounds. And force dy equals negative 200 pounds. Okay, there's our free body diagram. Okay, so now our next step will be finding the resultant force by summing the x and y component of our vectors, okay? So we're going to flip this over. Go. All right, so now we're just looking for, again, our resultant force by summing all of our forces. Okay. Oops. Okay. So we have our, so we're going to sum force CX. Force CX equal 150 pounds. Let's say that was 300. Let's say 350 pounds. We call this 500 pounds. So my sum of, so my FX forces, some of our X's are 500 pounds. Now we have our sum. Y's. That'd be force CY plus force DY. We have 260 pounds. Plus negative 200. And that will be 60 pounds. And this will be going up. And this going to the right. Just like so. So our sense, oops. That's right. And up. Okay, now that we have solved for the components of our resultant force, I am going to draw a free body diagram of our resultant forces and solve for the magnitude of our resultant force. Okay, so again, we have our f of x. Sum of our f of x is 500 pounds. To the right, and we have our sum of our y's is 60 pounds up. Now let us solve for our resultant force, which is the magnitude of our hypotenuse. So we're going to call this 500 pounds. We're going to call this 60 pounds. And how are we going to do this? Equals c squared. Okay, so now that we have the components, I'm sorry, I had to take a break. So now that we have the components of our values for our components of our resultant, now we use Pythagorean theorem to find the magnitude of our resultant force. And given our math, the magnitude of our resultant force is 503.6 pounds. Now that we have the values of all of our sides, our last step is determining the angle. All right, so the way we can find the angle is that we can use our tangent trig formula, which is tan tangent theta, which is opposite over adjacent, which is 60, 500 pounds. And we're going to actually use the reverse tangent since we're looking for our angle. And let's go ahead and solve for that. Okay, so when we solve for the reverse tangent of find our angle, we get our tangent of theta equals 6.8 degrees. We'll just say 7 degrees. So our direction let's start with our magnitude. Our magnitude is 503.6 pounds. Our direction, 7 degrees counterclockwise. Positive x axis, and our sense is right and up. Okay, so that's how we find the resultant force of our force vector. Again, the steps. First, you want to determine the magnitude, direction, and the sense of the force vector. You want to solve for the component forces. You want to draw a free body diagram of the components of your force vectors. Next, you want to find the resultant force by summing all of the forces. After that, you're going to draw the X and Y components of the resultant force, then solve for the magnitude of the resultant force. Then lastly, you want to solve for the direction, then draw the resultant force. All right, the magnitude, your direction, and your sense. Okay, I hope this helps. Keep practicing, and you will be ready for our next step, which is our moments, and then we will be solving the reaction forces of a truss. Have a great day. Peace.